Okay, first of all, truly appreciate the invitation. It's a pleasure to be here. Since I arrived to Cardiff about 2 years ago, has been a wonderful ride so far, and I'm really enjoying my work. And it's as well a pleasure to be able to share that work with you, or part of that work with you. Okay, so, and I apologize, I wanted to introduce myself as well, what I do. It has been done, but nevertheless, so very quickly, I do look at ocean-lying volcanoes, typically look at them in a more integrated approach. And what really fascinates me is to see how these volcanoes are the result of deep internal processes, and yet they are shaped dramatically as well by external forces. And it's exactly this interface that's sort of drives my research, and with implication for hazards. I must say that I was mostly a volcanologist and volcanostratigraphy or volcanostratigrapher, but two events changed my career in terms of research. One of them was the eruption of this volcano here, Fogo, in the Cape Verde Islands, which I started studying and launched me in looking into active eruptive processes. And the other one was the collapse and tsunami generated by the same about 73,000 years ago. So this is how, with my background, I started working also in tsunamis, which was something I didn't initially planned or intend. It was, I came into this science a bit by accident, if I may say. And just to understand a bit of what I do, so I am primarily a field geologist. And so most of my research is very field intensive, and I also use geophysical, geodetic, and remote sensing surveys to complement my geological observations. I typically, because I work with volcanic islands, I typically use onshore, offshore approach. It's completely impossible to look at volcanic islands without seeing the submarine part, which actually is the greatest portion of that volcanic edifice. And because of that, my research is highly collaborative and multidisciplinary. I often use geochronological and geochemical tools to study the process I'm working on, in order to be able to quantify and identify events, look at, for example, the event frequency, return periods, etc. And then a lot of my work is to provide physical evidence onto our colleagues that do the numerical modeling of many of these processes in order for us to draw conclusions in terms of what's the hazard posed by these events and these volcanoes, etc. Okay, so although I'm not primarily a modeler, a lot of what I do is to feed in terms of physical parameters into model making, if I may say so. My view is that we only know if a model is approaching reality if we have physical constraints derived from the field, etc., in order to test those models and in order to make sure that actually those models will reproduce something that is more realistic than simply, if I may say, a more wild exploration of consequences. Okay, so this is really strong in my research, providing the physical evidence to then test models that will then eventually be useful for example, civil protection authorities, or to forecast the impact of hazards, etc. So it's kind of within this context that when the Tonga volcanoes started to erupt and created those series of tsunamis, we started to look at this. So this was a team effort. So the work was published roughly a year ago in Nature. And as I said, it's a team effort. The first author is Rashid Omira, my colleague from Portugal, from the Sea and Atmosphere Institute in Portugal. He's a brilliant tsunami modeler. Together with his postdoc, Jiwon Kim, are kind of the genius behind the numerical approach I'm going to be showing here. Also, Usama Kadri, here from Cardiff University, a mathematician and a world expert in acoustic gravity waves. And I apologize for the big word, the big expression, but you will understand that these acoustic gravity waves are super important in this particular case. And then also a colleague from the Canaries, Pablo, who's a works with remote sensing and satellite imagery. They provided also crucial input into the work. And then also Miguel Miranda, Fernando Carrillo, and Mariana Batista from the Portuguese and Atmosphere Institute, who also helped with providing the framework for this work, let's say. So before I jump in, I'd just like to say that what you're going to see is we were able to explain and put a working model within 1 month of this event. And that wouldn't have been possible if it wasn't for a fortuitous combination of factors. One of them is just we had just came out from a research grant led by Rashid Omire to look at what we call meteo tsunamis, so tsunamis generated by atmospheric sources, but particularly related to weather. Also a research grant or a project led by myself looking at how tsunamis can be generated by volcanic flank collapses and volcanic explosions. And finally, also the long-standing work by our colleague Usama on the generation propagation interaction of acoustic gravity waves in terms of detection of tsunamis, okay? If it wasn't for these three pieces of research that just came close to an end just a few months before the event, we wouldn't be able to actually put forward what you're going to see next, okay? So I wanted to establish this context before I jump into the science, because this is, I think it's quite important and interesting how sometimes is, you know, we have the expression that being at the right moment in the right place, etc. This is one of those cases in which our research was in the right moment in the right place in order to make this contribution. Okay, so volcanoes. We all know that volcanoes can be the source of tsunamis and powerful tsunamis. The one that is probably most known and to some extent also most controversial is, so if we have a volcano having a what we call a flank collapse, so a major landslide, either subaerial and submarine or just submarine or even just subaerial, but entering into the ocean, which will displace the water column and generate a tsunami that will have devastating consequences, certainly near field.
Sorry, we've got to keep a look up there.
It's gone again.
So I was saying, so flank collapse is one way and is known and to some extent is also a bit controversial of the magnitude of these tsunamis. But then we have other ways of, like, for example, pyroclastic flows entering into the ocean, or for example, underwater explosions in which Unga Tonga volcano also generated. In fact, Unga Tonga volcano probably combined almost all the mechanisms you see here. And then there's, for example, also if a volcanic column loses its sustainability in terms of the gases that are propelling it to the atmosphere, if that loses its strength, then the column can collapse and all that material will dislocate the water column to generate the tsunami. We can have also volcanic caldera collapse. In other words, seafloor changes, a bit like it happens with the tsunamis triggered by earthquakes. And finally, the most enigmatic of the mechanisms is what we call meteo tsunamis. So tsunamis that are actually generated by atmospheric waves that will excite the ocean atmosphere interface and generate the tsunami. We knew that this mechanism existed, but what happened is that we were never able to explain it properly. And moreover, all the historical examples that we know that possibly could be explained by this mechanism, they happened before a global wide dense instrumentation as we have nowadays with satellites, tide gauges, etc., dart buoys, etc. So all this global and wide instrumentation that we developed in the last 20 or 30 years nowadays put us in a very unique position to actually look at mechanisms like this one. And in this particular case, it's precisely what kind of what happened. So this was by far the most enigmatic mechanism, and yet it's, as you will see, and now hopefully will convince you, is the one that explains the tsunamis generated by the Unga Tonga volcano. Okay, so by the way, the volcano, the full name of the volcano eventually is Unga Tonga Unga A'apai. It has this very long name because, and shall demonstrate next, it was formed by two islands that got joined together. So Unga Tonga and Unga A'apai that got joined by a volcanic eruption recently, and so the locals decided to call it the whole island as Unga Tonga Unga A'apai. They're just the surface manifestation, a much larger volcano, submarine volcano, which I'll show you next, which we call Unga volcano. So for short, I will be calling it Unga volcano, and you'll understand what I mean with this. But when this eruption happened, it was quite clear that was unlike anything we've seen before, and this is well illustrated by the news titles that you see here. So the eruptions happened on the 15th of January 2022, and on the 17th of January, it was quite clear, there was already new science, volcano eruption in Tonga was a once-in-a-millennium event. The other quite interesting aspect of this eruption is that it created these puzzling ripples in the Earth atmosphere, which will be very relevant for what I'm going to talk next. And this was immediately recognized, went into the news as well. And it was a style of eruption, again, different to some extent of what we had seen before. It was a colossal hydromagmatic eruption that produced also quite a lot of steam. If we look at the size of the eruption, so we volcanologists have a measure to compare the size of eruptions, explosive eruptions, by the quantifying the amount or the volume of ejected material by that eruption, and we call this the volcanic explosivity index. An interesting thing about this eruption is that because most of it was steam, the volume of ejected material is actually fairly small for the size of the explosion that happened, okay? And typically, the volcano explosivity index can be equated with a column height, and this was the highest column ever recorded in modern times. And yet, in terms of the ejected material, so the solid material ejected by the volcano is actually much smaller than many other eruptions we've seen. So this was a completely different beast in terms of volcanic eruptions. And this is why immediately on the news was why the Tongan eruption will go down in the history of volcanology, because it forced us to look at a different type of eruption that was not well characterized, or for which we were not exactly expecting until the event happened. Okay, so bit of context. So Unga volcano is located in the Pacific Ring of Fire, as you know, and in the Kingdom of Tonga, which is located and is part of the Kermadec Tonga interoceanic volcanic arc. So
in the garden, I've got my phone. Ring me if you want anything.
So the Tonga Trench and the subducting Pacific plate is going underneath the Australian plate, and because of dehydration, will reduce the melting point underneath the volcanic arc and creating the magmas that will create the volcanic arc. And so Unga volcano is part of this reach. We call the Kermadec Tonga reach, and it's an interoceanic volcanic arc associated with a subduction zone, as I mentioned, along the Tonga Trench. Okay, so as I mentioned before, the Unga Tonga Unga A'apai is just the latest manifestation of the larger Unga submarine volcano, which you can see here. It's a really large volcano with a central caldera, and the two islands, Unga Tonga and Unga A'apai over there, they were the ones, they are located in the rim of this caldera. And then in 2009, there were several eruptions in the historical period. The latest ones were 2009 and 2014-15, and then again in 2021 started new eruption. it was the 2014-15 eruption that actually connected the two islands and gave the name to the volcano, the combined name of Unga Tonga, Unga A'apai. And in fact, the satellite imagery that you see here show that. You have the two islands before, and then this eruption created a cone that connected the two islands, and which became known as I said, this Unga Tonga, Unga A'apai. Okay, so after a period of quiescence, hydromagmatic activity resurged again in, as I said, in December 2021, and then it went into a quiet period. And then again, on the 14th of January of 2022, restarted again. And this imagery you can see here is taken on the 14th of January, showing the resurgence of the explosive activity of the volcano. And then you can compare how the island actually evolved on the day. So this satellite image is from the 7th of January. This is on the 15th of January, just before the main explosion, the one that I'll be talking about in this talk. This was just a few minutes actually before that main explosion. So the hydromagmatic explosions had already disrupted this cone that existed here and separated the two islands again. And then after the colossal explosion that we'll be discussing, so this image is from the 18th of January, basically all the rest has disappeared, and even the original two islands are reduced in size, especially Unga A'apai. Okay, so what actually happened was on the 15th of January around 5 p.m. local time, there was this colossal hydromagmatic blast or eruption. In fact, we now know it was not just one blast, it was basically a series of blasts in very short time. That this is the one that created a large plume and volcanic cloud that we've seen on the satellites, and that basically created the tsunamis and which call everyone's attention. A recent survey shows now that this colossal explosion created a massive caldera. Well, the caldera already existed, but the explosion basically removed a lot of that material, making it way larger, showing that this was actually a really massive volcanic event, more than eventually one would judge just by looking at the explosion of the volcano themselves. I just been in a workshop in Germany a few weeks ago in which they documented submarine mass transport flows, so submarine avalanches related to this eruption, which cut 2 or 3 submarine cables that gave internet to Tonga. And because the submarine mass flow along its way, it cut the cables successfully, we can calculate its velocity. And the velocity calculated for that submarine flow was 130 kilometers per hour. This is way faster than anything recorded before in terms of what we normally call turbidites. So the submarine mass flows that go along the seabed, typically triggered either by earthquakes, in this case by a volcanic eruption. Okay. Excuse me. So when this eruption happened, or when this explosion happened, it was immediately recorded by worldwide satellite networks. It's the largest explosion recorded in the atmosphere by modern instrumentation, is equivalent to 60 megatons of TNT. So to put it in context, equivalent to maybe 50 Hiroshima bombs. And the erupting column reached around 57 kilometers into the atmosphere. So injecting material through the stratosphere into the mesosphere. And the aerosols produced by this eruption are still in the atmosphere as we speak now. So this is a series of these satellite images that basically show this blast, let's say, of this massive explosion that happened on the 15th of January around 5 p.m. So the explosion itself created a tsunami. Okay, so this underwater blast created what we would call a more normal tsunami, in the sense that It was generated by the dislocation of the water column. And this has been simulated by our colleagues. They basically showed this about 100-meter projection of the water column up, which explains the observations, the near field observations on the impact around Tonga. Okay, so the first tsunami to arrive, actually not the first tsunami to arrive, but one of the main tsunamis to arrive to Tonga was actually generated by this mechanism. But we didn't study this mechanism in particular. We were looking at the global signal, but nevertheless, just to, as I mentioned, this eruption created included several mechanisms of tsunami generation, including the one I show here. And in fact, there was a refinement later on and published in a recent paper by our colleagues in the United States that showed actually that this what we call a big blast was actually a series of basically 3 big blasts with just a few minutes or so in between them. So the first one was at 4:45, the other one at 4:58 and 5:44. These are UTC times, not local times. But you can see that there was just a few minutes in between those 2 blasts, and then a bit less than an hour to the third blast. And when you look at the tide gauge records in Tonga, you can see the signature of the tsunamis generated by these blasts directly. And in fact, one of the tide gauge basically failed because it was destroyed by the tsunami. Okay, so again, this is just to show that we are still distilling what happened, particularly in the near field. And because it involved all these different mechanisms, it has been proving quite challenging to be able to separate what different mechanisms created in terms of tsunami and how those tsunamis basically added or canceled themselves eventually to produce the observations in Tonga. Okay, so what about the far field? What about what was recorded in distant shorelines? Okay, one of the things that really called my attention, and my colleague Rashid at the time, I mean, we were looking at this just a few hours after the explosion went into the news, and we immediately recognized that this was different. And the reason for that is so this was published on the 15th of January or soon after, actually it was the day after. And what's really called our attention is the fact that, so the tsunami happened here, but it went really fast and created destruction in places that we were not expecting to create destruction. Like for example, the tsunami in Tonga, as you can see in these images, basically the same magnitude as it happened in Peru, which we would not expect because the wave would dissipate its energy. And it also created havoc in New Zealand, but also in Japan. And so it was quite clear that this tsunami was traveling much faster than a normal tsunami, if I may call it like that, and that unexpected wave heights in very distant shorelines that, again, we were not expecting to see in a normal tsunami that basically dissipates its energy fairly fast. So what we've done is grab a standard tsunami propagation model as we use for normal tsunamis, earthquake-triggered tsunamis or volcanic-triggered tsunamis, but what we call a point source tsunami. So basically, the dislocation of the water column by either a volcano or an earthquake, and see how that ocean gravity tsunami, as we call it, would propagate. And what you see here is in colors, and the contour lines, they represent the tsunami travel time. So the time that the tsunami takes to arrive to a particular distance from the source. And all the dots are tide gauges and buoys and places where the tsunami was recorded with its time. And one of the things you will notice immediately in this map is there's a mismatch between the colors of the background with the colors of the dots. In other words, there is quite a delay on the propagation of a normal tsunami compared to the observations we see worldwide. And this is particularly acute here in the Atlantic, for example. The tsunami arrived to Portugal and the Azores, etc., almost 10 hours or around 10 hours earlier than a normal tsunami should be arriving, particularly because a normal tsunami would have to go around Cape Horn to enter the Atlantic and then go and propagate from the south to the north in the Atlantic. And this, of course, causes a delay, if I may say so, that is certainly not compatible with the arrival times we see in the Atlantic and in many other places as well, in the Indian Ocean and the Pacific. So again, this immediately is showing that whatever is driving this tsunami cannot be explained as a conventional tsunami, let's say, what we call an ocean gravity tsunami. So just propagating at this normal speed under gravity and the influence of gravity. The other thing that also is illustrated here is if you look at the tsunami wave amplitude along the distance as a function of distance to the volcano, you will see that, for example, Tonga had basically the same wave amplitude, or if you want wave height, than Chile. And for example, Portugal and the Y also had similar wave magnitudes. And this is really odd. This is extremely odd. This is basically showing that what we saw in the news, so this is the physical evidence that shows that what we immediately suspected just by looking at the news, how they were being reported. So if this cannot be explained by a normal tsunami, we need to find a way to explain it in a different way. Okay, so as I mentioned, this explosion was the source of really puzzling ripples in the atmosphere. So it created all these waves due to the explosion that go from what we call shock waves, which travels faster than the speed of sound, including what we call acoustic gravity waves, which basically travel at the speed of sound, and eventually many other waves. And I want to focus on particularly on this type of waves, the acoustic gravity waves, which are what we call a low frequency compression type sound waves propagating under gravity. So they are traveling at the speed of sound, as I mentioned. Okay, and what you see here in this animation is the same you've seen before, but using the satellite imagery with. So this is, apologies for the cut in the scale. This is what we call the top of the atmosphere brightness, which is a measure of temperature. But the main thing I want to show you here is, if you look, you can see these waves propagating and moving the clouds with it. You can see it, for example, now here, and they are propagating faster than the volcanic plume itself. These are the acoustic gravity waves, which are going to be crucial to this tsunami generation that I'm going to mention. Okay, and these acoustic gravity waves actually went around the Earth several times. This is an animation that was done by our colleagues in MIT. You can see how the waves are being propagated from the source, and then as they travel, they go around the globe. Okay. The next animation as well shows this and shows basically how it goes to the other side of the globe and then eventually comes back around. And it went 3 or 4 times around the Earth until eventually dissipated. And our own satellite imagery also shows this. So you can see the wave going into basically to Europe, to the Antipodes, and then coming back is a bit more faded, coming back into its origin. And in fact, as I said, this went around the world several times. Okay. These acoustic gravity waves, as they travel, what they will do is they will cause a jump in the air pressure as they travel. So the front of the wave will cause the air pressure to have a disturbance. That disturbance can be measured by normal atmospheric barometers, and the world is covered in weather stations that nowadays measure air pressure, and many of them measure almost at every second or minute or so. So we can actually look at how these waves propagated throughout the globe. Okay, and so you can see how these waves propagated are here in red lines. But what I wanted to focus is in this graph here, which shows, so on the upper part of the graph, what you see is the unfiltered atmospheric pressure record. So you can see how there's this diurnal pattern as you expect. The air pressure typically lowers during the night, increases during the day, and so on. But you see this massive jump that was recorded worldwide And in fact, as the waves went around the globe several times, so you have a first jump, okay, which is marked in red, and then you have the one marked in orange, which is basically, so this one is the first arrival coming in the most direct and shortest route to your point. And what's here marked in orange is the same wave, but going on the farther side of the world until it reaches the point. Okay, and then in yellow is the first part of the wave, but once it passed the entire globe and then is back to that point. And what this graph shows as well is on the bottom is the filtered tide gauge on these several locations. And what you can immediately see is every time this pressure, we see this pressure jump. In other words, every time one of these acoustic gravity wave fronts is passing on the point, we have the generation of tsunami as recorded in the tide gauges. Okay, and one interesting thing as well is that in some places, it's not even the first wave that creates the largest tsunami. It can be the second or the third. For example, here in the Caribbean, you can see the amplitude of the tsunami here. The bottom is way higher than, for example, the first and the second arrival. Okay, so this tells us a lot about the mechanism it forms. The other thing I would like to point out in this graph is as you move towards from New Zealand to Hawaii, Caribbean, and Portugal, you're getting close to the antipodes of Tonga volcano. In other words, to the other side of the globe, the far side of the globe of where the volcano is located. So it's no wonder that in Portugal, for example, the direct arrival and the more distant arrival of the same wave, they're going to almost coincide because they are very close to the antipodes of the volcano. And actually, the antipodes of the volcano is located in the Saharan desert, because if it was located over ocean, maybe would have been interesting to see what would be the magnification of the tsunami by the convergence of those two acoustic gravity wave fronts. But the key message here is that this clearly shows that the atmospheric waves and the tsunamis are related, because they are arriving at the same time almost or basically everywhere. Okay, so again, they must be related. So what we suggested is, as the eruption created these acoustic gravity waves, the explosion created these acoustic gravity waves, they will excite the ocean atmosphere interaction. And as the waves propagate, they create the tsunamis, which is what we see in the first arrival in the tsunami record. But interesting, we have this larger group of waves, of tsunami waves, at higher amplitude coming next, which are formed by a mechanism of resonance between the ocean and the atmosphere. So when we have these oscillations in the atmosphere crossing the ocean, if their wavelength and speed matches the speed and wavelength of the long waves of the ocean, they become in phase and they basically start. There's a process of magnification, okay? Interesting, this only happens in the very deep oceans, because it's only in the very deep oceans in which the waves are long enough and fast enough to have this process of interference with the atmospheric waves. Okay, so as you probably know, when a wave approaches shallower waters, it will reduce the wavelength and increase the amplitude. And for that reason, the long waves of the ocean created by atmospheric processes like storms and weather patterns, etc., they will only have a really long wavelength and speed in the very deep oceans that would match the same as the acoustic gravity waves. So this mechanism of resonance mostly happen in the deepest parts of the oceans and in deep open ocean, not so much near coastlines. And this will have really critical implications in terms of hazards. Okay, so when you look at tsunami record, you know the first arrival comes from the frontal part of the acoustic gravity waves. Kind of the second arrival that comes immediately afterward is generated by this mechanism of resonance that will amplify the tsunami waves. So again, and this shows that this tsunami was generated by a constantly moving source that instead of dissipating its energy is constantly pumping energy into the ocean and into the tsunami as it travels. Okay, in fact, we have shown this analytically, and I apologize for the very heavy maths that's in this contained in this slide. So what here on the upper left shows. So this is basically, as I said, is analytical model. So is adimensional. So what you have here is basically a distance and the amplitude of in this case, the acoustic gravity wave, and as time progresses. The lower part, what shows is the tsunami generated by this process. And so what this basically shows is that as the acoustic gravity wave is propagating, it will be followed. So the main envelope then will be followed by this reverberation created by resonance that will basically carry on beyond the frontal wave of the tsunami. Okay, so we've shown mathematically or analytically that this is possible, and the way to explain is that this keeps pumping energy into the waves as the waves propagate, and it will take much longer to dissipate compared to, let's say, a normal tsunami. So now, how can we then simulate numerically how this propagates? Well, so the key is probably the lower part of this graph. What we've done is we have all the atmospheric pressure gauges records. So we know how the pressure variated as it traveled as a function of distance. So we could reconstruct these waves in terms of atmospheric pressure, because now we know the mechanism that creates a tsunami. We can then simulate the tsunami like in this manner. So what you see in this lower part of the graph is the propagation of the atmospheric waves in the upper in yellow and orange, and lower down the tsunami. In the very top of this figure, what you see is again the tsunami travel times by this new mechanism compared to the observations, and you will see that the colors match. Okay, so we get exactly the time we would expect of arrival, for example, in the Atlantic, matches the observations if we use a model like this, if we explain the tsunami like this. And one thing I would like to highlight here, this tsunami is traveling at the speed of sound, as acoustic gravity waves travel at the speed of sound. So the tsunami is traveling also at the speed of sound, which is about 3 times faster than a normal tsunami. And that's what it explains why a normal tsunami would have a delay compared to the observations, but in this particular case, it doesn't. Okay. One of the things I will also like to call your attention, and the next slide will show an animation of the propagation of this tsunami and etc., is because the tsunami is triggered by this coupling between the atmosphere and the hydrosphere, it doesn't need to go around Cape Horn. It can simply jump between dashes, the Isthmus of Panama, into the Caribbean Sea, into the Atlantic, and start propagating on the other side of the Isthmus of Panama. And that's what also we want to see in the next slide, and I'll be calling your attention to that. Okay, so, apologies, before that. What this graph shows is, in black is the propagation of our own acoustic gravity wave tsunami. In blue is what would be the tsunami travel times as a function of distance for a normal point source tsunami, and in red are the observations. Okay, and you can see that our model in black matches much better the observations than the blue one. Now, I'm sure you're going to ask me, what about, there's a lot of these red dots that, first of all, have a very large uncertainty. True. It's because most of those tide gauges, their record is not, they only measure, for example, every 15 minutes rather than every minute or so. But there's also another reason why you have all this dispersion, is that once a tsunami arrives, for example, in a harbor, there will be all these refraction processes because of the shape of the coastline, etc. Also, many of the tide gauges are located in very protected areas in harbors. So all this will induce a certain delay on the tsunami that is a local effect and not exactly the real tsunami travel time of the tsunami. But nevertheless, the black dots are a much better fit to the red dots if you take into account they're the ones that have a very small uncertainty, here represented by the error bars, as compared to with the blue ones. So again, showing that an atmospheric source can explain this tsunami actually quite well. Okay, so sorry. Oh, there it is. Okay, just to show my point as well, this is what would be what we call a point source tsunami, so normal tsunami generated, and what would be the effect across the world or the Pacific. And you can see that basically a normal tsunami would affect New Zealand, maybe Australia, Fiji, etc., but not beyond that. It would never reach Japan, would never reach Chile, certainly would never reach the Atlantic. And I would like to call your attention that in the Atlantic, the tsunami was 50 centimeters. In Portugal, for example, it was 50 centimeters. It might not sound much, but it's for something that was generated in the very far end of the world, it's quite something. So this is the animation I was telling you about, and you can see how, as the atmospheric waves propagate on the top, the tsunami is propagating and then also coming back. And again, it shows this effect I was telling you of how it goes over the Isthmus of Panama. Okay, so stop here. So you can see the first gravity waves front arriving at the Isthmus of Panama. And when I play it again, you will see how instead of the tsunami going around this, basically the tsunami will start again. We'll start here. So sorry, on the top is tsunami, on the lower part is the atmospheric waves, and not as I was saying. So you will see how really the propagation into the Atlantic is different than a normal tsunami. Okay, oops, sorry. So there it goes. Crosses the Isthmus of Panama, propagates into the Atlantic, comes back, crosses it again, and then back to the source. And this I went around several times until it dissipated. Okay, so in terms of hazard implications, I go back to what I said. So resonance happens mostly or is very effective in deep waters when the speed and the wavelength of the gravity waves, the acoustic gravity waves, will match the long waves of the ocean. Okay, so a normal ocean gravity tsunami travel at the speed which is equivalent C here, and in which G, of course, is the acceleration of gravity, and H time, and so the distance. Sorry, so they reduce the speeds when they gain amplitude at shallow waters, and that's how it explains. For example, in a normal tsunami, you get the highest waves when it's arriving to the shoreline, but this is the opposite. This tsunami is the opposite. So this mechanism doesn't happen in this tsunami, except for eventually secondary triggered tsunamis. But the main tsunami, basically, they travel at around 1,000 kilometers per hour. So as I said, close to the speed of sound, showing no marked decrease in speed from deep to shallow waters. But because the resonance is not effective at shallow waters, in land masses that have really wide shallow water continental shelves, like the United Kingdom, there's almost no tsunami. In fact, the tsunami was not recorded in the United Kingdom almost anywhere, precisely because with this mechanism and because of the very wide continental shelf that the United Kingdom has, or the Great Britain has, and Ireland, this mechanism basically dissipated. The resonance stopped happening and the mechanism dissipated. And so we only had the first arrival, which was really small as compared to the higher amplitude resonance tsunami that comes afterwards. So in terms of hazard implications, it's quite obvious that where you're going to have the highest impact is in those land masses that are really close to really deep oceans, like, for example, mid-ocean volcanic islands, or, for example, all the land masses that are close to ocean trenches. And that explains why the highest tsunami waves were, for example, around Tonga, naturally, but then in Japan, in the Aleutian Islands, and in the coast, the western coast of South America, because you have the really deep waters of those trenches, and therefore the resonance mechanism is really effective in this areas. And one of the things I would like to zoom in a little bit here, and that's what's shown on the upper part, Because if you look at the bathymetry around Tonga, on the eastern side, and in the Pacific plate, the seafloor is way deeper than on the western side, which is in the Australian. And so when you look at the tsunami wave heights, as you can see here in this map in the middle, the highest waves will go to the east rather than the west, precisely because this resonance mechanism is much more effective to the east than to the west, because of as a function of the ocean floor, and therefore it's quite clear that the land masses that are more in peril for this type of mechanism are the ones that rise abruptly from the abyssal plains or from the deep ocean trenches, which is in total contrast with normal, let's say, triggered tsunamis. Okay, so to finish, Tonga tsunami is the first global volcano-triggered tsunami recorded by modern worldwide dense instrumentation. It was driven by this constantly moving atmospheric source in which the acoustic gravity waves radiating from the explosion, volcanic explosion, will excite the ocean and keep transferring energy into the tsunami by means of this mechanism we call resonance. And it also shows that violent volcanic explosions can cause fast-traveling, fast-reaching, and enduringly high tsunamis through this process I just described, and with clear hazard implications, which is it's the land masses that are next to the deep ocean that are more at peril from these mechanisms than others, for example, that are surrounded by shallow continental waters. Okay, so with this, I would just conclude to say that now we do have a model which environmental agencies, civil protection, etc., can actually use, and volcano observatories, tsunami warning systems can use to account for this type of tsunami. So the model is available, and as soon as there's one volcanic explosion or so, we can run the model and see. It will be maybe won't be on time for the near field, but certainly could be on time to raise the alarm for the far field. And I would like also to say that our colleague Usama Kadri in mathematics here at Cardiff developed a tsunami warning system, or is in the process of developing a tsunami warning system that uses the acoustic gravity waves and doesn't care about what's the nature of the source, because the acoustic gravity waves can be recorded in hydrophones and in many other instrumentations that we use, for example, to monitor nuclear explosions and nuclear tests. And using that, we can actually create a tsunami warning system that doesn't care about the source, if it's volcanic or earthquake, because all of them will actually create acoustic gravity waves. And as soon as those acoustic gravity waves are recorded in those sensors, then we can immediately then compute what would be the potential tsunami and raise the alarm. So this research is at, I would say, upstream and at the forefront of the next generation of tsunami warning systems, hopefully, not only in terms of volcanic triggered tsunamis, but also in, for example, earthquake triggered tsunamis. So the lessons we've learned from here can actually be implemented and applied to with a much wider implications than just looking at volcanic triggered tsunamis. That's all I have to say. Thank you.